I want to start with a recap of the notation that we introduced last time. So this is our mapping notation, and this is a proposition. It says something, it asserts something, that f maps x to y, and what that means is three things. So I always think of this as, I'd always remember what this means by remembering that it means three things. Something related to f, something related to x, and something related to y. So it says f is a function, which itself means two things. F is a set of pairs, and it satisfies that for all x, y, z function condition. Secondly, f maps x to y means the domain of f is x. And thirdly, it means the range of f is a subset of y. So usually the way I think about these three aspects of f maps x to y is I think of f is a function as telling me that f maps inputs to outputs. So f is a set of pairs, but not just any set of pairs. It's a set of pairs that I can think of as associating inputs to outputs, so that I can evaluate f at inputs and look at f of x for some little x that is a possible input. And then I think of this as telling me what are the possible inputs. So here big X is the set of possible inputs, the things that could be inputted into f to get outputs. And then this last part tells me some information about the outputs. It tells me that the outputs all end up being in y. So one thing to keep in mind is that the information you have about x is sort of a two-way statement. It's an equality, so both inclusions, whereas the information you have about y is a one-way statement. When you've got the mapping statement here, f maps x to y, you have a two-way information about x and one way about y. So what I mean by that is, if you're thinking about what are the possible inputs, you know both that all possible inputs to f live in capital X, and that everything that lives in capital X is a possible input to f. On the other hand, when you think about the outputs of f, anything that arises as an output, like something that you get by doing f of something, is going to be in y. So all the outputs of f are in y. But you don't have necessarily the converse. You do not have that every element of y arises as an actual output. So there could be some elements of y that are not f of anything. So that's pretty much how I think about this. Now I want to spend the rest of this video giving you kind of a different or additional way of visualizing f maps x to y. Okay, let's say f maps x to y. Let's say we know that information. So f is a function, inputs come from x, and everything in x is an input, and outputs all live in y. Now, x and y are sets, and so is f. F is a set of pairs. But I want a better way to visualize what is f in this context. Now, all I know about x and y is that they are things in set theory, so they are sets. So they have some elements, right? And often the way I visualize sets is as like a container with the elements inside. So I think of these like dots in there. So maybe x consists of, let's say, three distinct things here: little x, little y, little z. So then this is a situation where x happens to be this. Y is also some kind of set. So let me imagine that y consists of little a and little b. So that would be this situation. So I'm just making stuff up. Suppose f maps x to y, suppose x is this and y is that. Then what is f? So this picture is now missing f. It contains a nice depiction of x, a nice depiction of y. But how do I depict f? So, well, one way I could go, I mean, f is a set, right? So one thing I could do, let's say f is this. It's a set of pairs. So let's say it consists of x, a, y, b, z, b. Let's say this is f. which, by the way, this is a valid choice of f, which I'll discuss in a moment, why when you know this, it's in fact true that f maps x to y. But let's say this is f, then how can I depict f? Well, a first thought might be, well, f is a set, so just give it a nice blob, and then just name the elements these pairs. But I do not recommend thinking of it this way, even though you can. No one picture is more or less accurate than another here. Still, I would say that there's a better way to visualize the relationship between f and the other things in this picture, which is the following. Every time you see a pair showing up in f, draw a connection from, draw an edge, a connection from the left coordinate, x, to the right coordinate, from the first coordinate to the second coordinate, like that. So this represents the presence of the pair xa in f, and then the presence of the pair yb, and then zb. So this is a way of thinking about what f is. It's these green arrows. That's kind of f. Like, yeah, it's a set, so it is a container containing these objects, but actually, maybe a nicer way to think about this container is, instead of thinking of it as containing these dots, think of it as containing these arrows, and these arrows bear some relationship to x and y. Okay, now about my, in this setup where I'm just making things up, I'm just making up what x and y are and what f is, there is one part that I shouldn't be making up, which is, if I'm going to say that f is this, and I'm also going to say that f maps x to y, we should make sure that I'm being consistent. If f is this, then is it really true that f maps x to y? So let me verify without proof. So not really a proof verification, just an inspection that it's a reasonable picture. So proof would probably involve lots of cases, since f is the set of things that are either equal to this, or equal to this, or equal to this. Okay, so firstly, is f a function? So you look at this, you check, yeah, that's a function. Secondly, is the domain of f equal to x? So what is the domain of f? It consists of these things. So the domain of f would be this set, right? Which is indeed x. Okay, so you see, that's why when I came up with this example for f, I made sure to include a pair that has x as the first position, a pair that has y, a pair that has z. And finally, is the range of f a subset of y? Yes. In fact, if you select these, the range of f is y, right? So we have more than just the range of f being a subset of y. We have, in this case, the range of f equals y. Okay, so the picture is consistent. Now, actually, these kinds of pictures you can draw for any set of pairs if you want to. So in this context, where f maps x to y, you specifically have f is a subset of, well, you more generally have that f is some subset of this Cartesian product, right? The collection of all pairs whose first coordinates come from there and second coordinates come from there. But in addition to f being a subset of this Cartesian product, additionally, it's also a function. This is one of the things you show on one of your homework problems from last time. So let's make the discussion a little bit more general so that we can discuss all kinds of situations using these nice pictures. So even situations where you're not looking at a function. So again, say x equals, so by say I just mean let. It's the same thing. Say is just supposed to suggest that we're kind of making this up. Let's say big X is little x, little y, little z, just like before, and big Y consists of little a, little b, just like before. Then we can depict subsets of this Cartesian product using diagrams with arrows. So how about this? By filling the following diagram with arrows. So what we're doing is coming up with a picture that helps us, point to things and reason about things. It's not going to help us write a proof, since proofs are going to use definitions and axioms and theorems. But it will help us to imagine things, which can indirectly help us write proofs. So take this diagram, and then anytime you have a subset of this Cartesian product, then you have a set that consists of some pairs, all of whose first positions are going to be one of these dots, and second positions are going to be one of these dots. So you just fill this with edges, arrows, or edges maybe is a better term. So like if the pair x comma a is in there, is in a particular subset, then in your depiction of that subset you would include that edge. So let me give you an example. Let's say f is, so let me make it be in green. Let's say f is the following. Let's say f is this. And if you look at the elements of f, they are all elements of this Cartesian product. And so they are all, and so f is a subset of this Cartesian product, right? So we have f is a subset of this. And this Cartesian product has up to six elements, and f seems to contain probably 3 of them here. I say probably because I never put any assumption that anything is distinct from anything else. So how about I actually put that assumption? Okay, so assume x, y, z, a, and b are distinct. So things that are represented by different letters of the alphabet really are different here. Okay, so f contains 3 out of the possibly 6 pairs that it could contain. Those 6 pairs that it could contain are represented by the 6 possible edges that you could draw, right? There are 3 like that, and 3 like that. So that's the 6 pairs, x Cartesian product y itself, you would depict like that by including all of those. F only consists of these 3, so I would depict it like this. So this is a picture of f. And here, would you say that f is a function? So what do you think? And here's my answer. I would say f is not a function, and now I can point to a nice part of the picture to say exactly why not. It's this. So right there, that's the issue. And anytime you have something being not a function, this is the kind of picture you would see when you think about this way of visualizing things. That you've got one input that's heading out and mapping over to 2 different things. So it seems that f cannot make up its mind as to whether x should get mapped to a or whether x should get mapped to b. So this is the picture of not being a function, kind of. So due to this, f is not a function. And yeah, sure, you could also look at the list of pairs and just be like, look, it contains the pair x comma a, it contains the pair x comma b. The first positions match, and the second positions are non-equal since I assumed everything here is distinct. So you can think of the assumption that everything is distinct as sort of telling us that the dots in our picture, or in our visualization, the dots that we draw as different really are different. Otherwise, without that assumption, how do we know that A isn't equal to B? Maybe the picture is deceptive in trying to label these as 2 different dots. Really, it's 1 dot with 2 names. So now I'm going to draw, using this way of drawing things, I'm going to draw a bunch of possible subsets of the Cartesian product, x product y, where x and y are the same thing that you see on this slide here. So I'm going to draw them, and then I'm going to ask you some questions and see if you can get them. So here's the first one. And my question for you first is, what set of pairs does this picture represent? So what is the green part representing? Okay, and here's the answer. So for all of those, I'm kind of expecting you to pause and try it if you want to, or whatever. You're in control. So should be this. Good. And now I'd like to ask, do you think, so given this picture, or this way of looking at it, whatever, do you think f maps x to y? So this is my question. Do you think f maps x to y? And by the way, x is still this, and y is this. So we still have that this blob is x and this blob is y, consisting of these items. So do you think f maps x to y? And here's my answer. Yes. Definitely f maps x to y. There are three things to check. F is a function. Yeah, it's a function. From the picture you can see there's none of this kind of nonsense, right? There's no one dot on the left with two things coming out of it. Second thing to check, x is the domain. Yep. The domain is, all of the left positions there. That does really consist of x, y, and z. So picture-wise, everything here has some green line coming out of it. And final thing to check, the range is a subset of y. Here the range is singleton A, and that really is a subset of y, right? Singleton A is a subset of doubleton A, B. So yes to this. Okay, new question. Or actually, new question for a new example. Okay, here's the example. So first try to write what set of pairs f represents. And here it is. We've got xa and zb. And then, do you think that f maps x to y? So what do you think about this? And my answer is no, this is actually false. And why is it false? So there are three possible ways it could be false if it's false, since this is a conjunction of three things. It could be false because f is not a function. That's not a problem here. F definitely is a function. It could be false because the domain of f is not equal to x. That's the problem here. It could also be false because the range of f is not a subset of y. But it is here. There's no problem with that. So this is false because the domain of f is actually just consists of these two, and that's not all of x. So from the picture, what the issue is kind of that there's something in the left-hand blob that doesn't have a green line coming out of it. Notice that this one, there was no problem with saying f maps x to y, even though there's something in the right-hand blob that had no green line coming to it. So that goes back to what I was talking about with this mapping statement, sort of making a two-way assertion about x while making a one-way assertion about y. So with x, you need everything in x to be in the domain and everything in the domain to be in x. With y, you only need everything in the range to be in y, not necessarily conversely. Another thing to notice is that this kind of thing prevents f from being a function. So it prevents you from being able to say f maps x to y, while this kind of thing is no problem. That did not prevent f from being a function. So you don't treat the left side and the right side the same when you're talking about mappings. Inputs need to get associated to outputs. It's okay if multiple inputs get associated to the same output. What's not okay in terms of mappings is to have one input where you can't make up your mind as to where it goes. So maybe it does make sense to actually call these arrows rather than edges, since they go left to right. You can think of them as being sort of labeled by arrows. The inputs go to the outputs. So here, starting from x, where does it go? What is f of x? Is it a or is it b? Unclear. F is not a function. There's no such thing as f of x. Here, if f is this, what is f of x? Clearly, it is clear that it is a. There's no doubt about that. What is f of y? It is clear that it is a also. There's no doubt about that, and there's nothing wrong with f of x equaling f of y. Okay, in the next video I will introduce some more kinds of things that you can say beyond just f maps x to y, and we'll see what they look like in the picture. So one of them will say things about situations like this where you have lots of multiple outputs coming to the same input. It'll say things about that, and another one will try to treat the y kind of in a two-way, giving it a two-way treatment in the same way that x gets a two-way treatment. So you'll see that in the next video.